Paolo Pasquali from Sarmap, and the topic of this webinar is about which is the information that we can extract from SAR data to help the mapping and monitoring of agriculture applications. I don't know how many are familiar with, how many of you are familiar with SAR, but I will go quickly through some recap about SAR. SAR, of course, is a peculiar technology, and one main issue is that it's an active system. So if we consider an optical system, an optical sensor relies on an illumination source. So we need to have a sun that's illuminating the area we are interested to look at. And of course, optical sensors depend on weather conditions. If there is a cloud cover, if there is no illumination or no return from the terrain, of course it's not possible to get any optical imagery of our area of interest. SAR is an active sensor, so it's generating its own energy to illuminate the terrain, but also using microwave frequencies, it's capable of penetrating through clouds. So we can have acquisitions over our area independently from the type of illumination existing or not, so day and night acquisitions, and even in case of cloud cover. That means that with SAR sensors we are more free to select the time of acquisition when we want to have an image over our area. And we know that this can be very important for agriculture. Agriculture is something that is changing very quickly with the time, and so we need to pick the data when at the right time when we need them. And so this is a particular feature that can be fulfilled, a particular requirement that can be fulfilled by SAR sensors. But what do we measure with our SAR sensors? Of course, we measure a backscatter reflection of our terrain to the of the illuminated energy, and the amount of the reflection we get back from our terrain depends basically on two physical parameters that are very important and that we can link very well to our agriculture. Of course, the first one is roughness. So the higher the roughness of our object that we are illuminating is, the stronger the radar backscatter. That means that if we have a very smooth terrain, of course we will get almost no reflection back. But we can think that as soon as our plants are growing, we will get more and more backscatter depending on the, say, size of the plant we are illuminating. So the second parameter that is to which SAR is sensitive is moisture. And of course, moisture is something that is changing very much along the life of the plant. So for instance, here we can see a time series of SAR measurements over the growth of maize plants. And we see that here we have actually the preparation of the fields. So here the peak of backscatter is mainly driven by the roughness of the terrain. But in this case, we see a growth, but also a change of the backscatter. And in particular here is due to here an increase due to the more water in the plants, and of course when the plants are ripe and they start to dry, the water content is decreasing and also our backscatter is decreasing. So we can link the backscatter to the amount of water that is contained in the plants. So basically if we repeat our SAR measurement through the whole growing period of the plants, we can extract a lot of information about the stage of growth of the plants and the stage of maturity and the type of water content that is in the amount of water content that is in plants. Well, Why are remote sensing data in general interesting for these type of applications? Of course, they provide geospatial information and temporal information. Geospatial means it's geo-referenced information, so very important is that we don't just get a nice picture, but pixel by pixel we will be able to locate accurately the measurement we make on the terrain. It's not just a single point measure, but we have, of course, images, so it's broad coverage, and so we can follow the spatial dependency of what is happening on our terrain. And of course, with the sensors we have nowadays available, also with the SAR data, we can get to very high resolution, to metric resolution. Very important is the temporal dimension that our data provide, and in particular is strengthened by SAR, in the sense that, as we saw at the beginning, of course, being weather independent, we can design our acquisition plan so that we have a full sequence of acquisitions over the full process we are monitoring. So we can follow the temporal variations of our objects. And of course, are not just pictures, but are physical measures. So if we are able to properly calibrate our measurements, we can get physical measurements out of our pixel values. Here just two examples to see that, of course, we are used to see, to look at optical images is something that our eyes are well trained since a lifetime to look at, so we can distinguish a lot of different things like fields, houses, and so on. Of course, to look at SAR data, we needed to change a bit our mind, our interpretation capability. In this case, colors are not given by the real different reflection, different wavelengths, but these are false color composite images. That means that the different colors come from different images acquired at different time. And so when we see that, for instance, here we have 3 images used to generate this color composite image using a red, green, and blue channel. If we see strong red, of course, we will see that the image acquired at the date of the red channel is stronger. So in this case, color means time. We see a stronger color that corresponds to the time when the corresponding image has been acquired. But if we switch from, say, the normal interpretation, so the human interpretation of the colors as for an optical image, we switch to the interpretation of the SAR data, so to the time interpretation of the colors, we see the amount of information that is contained in the SAR images that is also very, very big, so that we can follow, for instance, the different stages of growth of these serial fields, seeing red, green, and blue fields, looking at different stages of growth of the serials in the same image, the same area. And of course, this becomes quite extreme if we look at the large areas and at the large time scales, when we see all the growing stage of the different fields and the different species that are grown in this area. So basically, we are going to exploit these concepts, and we will look at practical examples. And a practical example where we are going to process SAR data using SARscape to investigate agricultural production in Southeast Asia. We are looking at an area in South Vietnam, so close to the Mekong River Delta. And of course, in this area, rice is the most important species that is grown, and we are looking at a quite small area with very high resolution data. What about? Here, as I said, we have mainly rice that is grown, but thanks to the favorable environmental conditions, rice is not just grown at one time, but is continuously grown. So in 1 year they reach up to 3-4 cycles of production of the rice here. So we have to look at we have to expect different growing stages in different fields. Yes, water is very important for rice, but not only for rice. So in this area there are also some fish farms, so there is some aquaculture going on. Shrimps and fishes are grown, so we need to discriminate from agriculture to aquaculture areas. We have 8 images available over this area. Cosmos SkyMed street map data with 3 meters resolution, so high resolution, and we have X-band data. X-band is a high frequency, very short wavelength, so we expect almost no penetration in the vegetation we are looking at. So all the reflectivity we are going to measure originates from the very top layer of the object we are looking at. This is very important because in this case we are looking at the small plants. We are not going to look at maize or even to dense vegetation like big trees. We are looking at small plants, so we need very strong sensitivity to changes in the backscatter. As an extreme, we could, if we would use L-band data over this area, so L-band has a much longer wavelength, almost a factor of 10 longer respect to X-band, we would penetrate through our vegetation and we would lose most of the information coming from the rice plants, in particular at the beginning of the growing stage. As we see, we have some river in this area. We have these that we will discover are agricultural areas, and we see a lot of fields that already pop up in this single image. But we have also little channels, roads, and some man-made features like small buildings along these communication areas. Okay. Let's start ENVI, let's start SARscape, and we will use one new feature of SARscape that has been introduced in SARscape version 5.1 that are workflows. Basically, all the processing will be guided by one workflow that will help to take track of all the steps we need for the processing and will handle all the file names and the symbol parameters. In this case, in this exercise, we will exploit only the amplitude of the SAR data, so we will exploit the so-called amplitude time series workflow of SARscape. So if we start it, we see that this dialog window will show up, where we see on the left all the steps we are going to execute today. Basically from the input, so that means from the preparation of our files we are going to process, we will be guided through multi-looking, co-registration, speckle filtering, geocoding, and extraction of some multi-temporal features we will use in the classification of our data. So all the procedure is guided by this workflow. Of course, the first step is to select our data. So here we have our images. We will start, as I said, from 8 images, and we see that in the name of the file we recognize the acquisition date. So we start from June 5th, 2013. Every 16 days we reach September 25th. So we have 8 acquisitions spanning about 4 months, and the growing period of rice is typically between 3 and 4 months. So these images are spanning a full season of rice. together with our data, we are going to perform geocoding, so correct from SAR geometry into map geometry. So we need to know something about our terrain. Of course, we can think that in this area we are mainly looking at a very flat area, but it's always important to introduce a digital elevation model in the processing of SAR data. This helps to get the precise geolocation of our data, to correct precisely the geometry of our data. And of course, we can input any DM we have available, but we can also exploit freely available information. So we can ask to the workflow to download SRTM, DEM for the area of interest. So of course, from the input files, the workflow knows which is our area of interest, and so we can automatically obtain this DM from the net. And we can select whatever cartographic reference system we want to use in our processing, and if we have no specific reason to select anything else, of course we can stay with the GeoGlobal, so latitude longitude cartographic reference system. So after deciding which DM we will exploit in the processing, we can have a look at the main parameters we can select, we can set to drive the processing. In this case, an important parameter is the grid size, the spacing of our geocoded products we want to obtain. Of course, 25 meters is not is too large for high resolution Cosmo SkyMap data, so we can decide to go for 5 meters resolution of our end product. And as I said, at the end of the processing chain, we will extract some statistical indicator pixel by pixel based on the time series of our data. So, for instance, we can extract the mean value of backscatter, the span, so how much is the variation of the backscatter from the minimum to the maximum in the whole time series, which is the single biggest variation, and other parameters that statistically, in a simple way, describe our time series. As said, these are the main parameters we can influence at the start of the workflow, but of course, through all the steps, we will have the control of each of the single parameters we would like to change. So after having selected these, we can switch to the next step, and so the input step of SARscape will start to search for the digital elevation model, to download it, to prepare it, and make it available to the processing. So after this phase, you see that the first step has been executed, and we will be ready to perform multi-looking. Multi-looking means, as I said, we start from complex data, but we are interested only at looking at the backscatter, so the magnitude of our data. And in this case, our data have a resolution that is even finer than the 5 meters resolution we want to obtain for our end product. So the multi-looking will perform a 2x2 average of our detected data, of our amplitude data. We see here that for each step, only the main parameters, the principal parameters, are presented in the view. But of course, if we are not happy just to look at the simple or the principal parameters, we can switch to the expert mode and see that we can control a number of parameters. So we have a fine control on all the single parameters if we want to perform it. In this case, for instance, you see at the end of the parameter list something about the type of acceleration we use in the processing. This is another feature that is new in SARscape 5.1. So a few steps has been updated, including the support of graphical cards, GPU processing. In this case, we see that actually the processing is exploiting my standard CPU in my laptop. So when we are ready of the parameters, and in this case, basically, we don't change any of the parameters because everything has been set automatically by SARscape, we execute the step. So basically now the program is extracting the amplitude and averaging it a factor 2 by 2. Of course, if we change the grid size we are interested at, the program will automatically update the multi-looking factor. When the process is ready, we have now a series of 8 images acquired on the same area, but they not necessarily correspond pixel by pixel one with the other, because they have been acquired with a slightly different geometry. So we need to perform co-registration. Co-registration is with SAR a process that is very much automatic. And so we can exploit this step to perform this co-registration without the need of manual interaction. And as you see, the amount of parameters that are really important to set in this case are, in the standard case, just one parameter. So if we have very high resolution data with a lot of topographic variations, we can even exploit our digital elevation model during the registration. In this case, of course, a flat area, the DM is not really necessary for the registration. In more complex cases where we have, for instance, very big variations of the images between one acquisition and the other one, we can go to expert mode and select a number of parameters, for instance, to increase the number of windows that are used during the process. But in this case, again, everything can be handled automatically by the program. So we are not going to change any of the parameters. So if we start the registration, the process will run automatically, and if everything goes smooth as it goes, we will get to the next step. You can see in the lower left area of the workflow window the preview option. So basically what I executed now is just the workflow without a preview, but of course if we are interested to look at the quality of the results after each of the steps, we can enable the preview option and the workflow will automatically load in ENVI the step-by-step results, and we can check the quality of the results. If we are not happy, we can go back another step and update parameters and run the step again. We have a series now of 8 co-registered images, and of course SAR is strange to our eyes also because it's typically affected by the speckle effect. It's something natural, but the result of the physics is that in areas with constant backscatter do not show with a constant gray level, constant values. But they have a variability, a kind of salt and pepper effect that is quite annoying to our visual interpretation, but also to the automatic extraction of information is reducing the accuracy of the results. Of course, at this point we want to reduce the impact of speckle, so we want to perform what is called speckle filtering. In SARscape you have a number of speckle filters that can be used depending on the case, in a case-by-case way. As soon as we have repeated acquisitions over the same area, as in this case, what we recommend is to exploit multi-temporal speckle filters. So basically, we want to identify homogeneous areas and filter them, and we want to discriminate small objects and not filter them. And this process can be very efficient and very precise if we exploit all the images we have available on the same area at the same time. Of course, if we provide 8 images in input, we will desire to have 8 images in output, so the filter is not mixing together the images during the filtering process, but is exploiting the images at the same time to optimize the parameters of the filtering. Again, in this process, I am not changing any of the default values because we are not in a very common, very standard condition. So even the number of looks, so the important parameter to drive the amount of filtering of our speckle filter is not changed. So -1 means that we are exploiting the default parameters derived from the ancillary information of our survey. So the program is filtering our time series, and after that process, we are ready to calibrate our data both in geometric and radiometric terms. So basically we are going from SAR geometry to map geometry, exploiting our digital elevation model and aiming to obtain data at 5 meters pixel spacing on the ground. Of course, we are also interested at calibrate radiometrically our data. That means that the final values we want to obtain in the pixels shall be physical measures. That means we want to get what is called typically sigma naught, so the backscatter coefficient. That is just a ratio between the amount of energy we use to illuminate the object and the amount of energy we get back reflected by these objects. So this number, that is of course in general a number smaller than 1, is our physical measure that relates with the roughness of our object, with the wetness of our object. So we want to perform radiometric calibration, and also we want to perform some additional normalization to try to cope with the natural variability of the backscatter from near to far range. And to ease the physical interpretation of our signal, we are happy to obtain data in dB, decibels. So we will measure values like minus 20, 15, minus some dB. Of course, as I said, sigma naught is a measure that is typically smaller than 1. So if we express it in a logarithmic scale, the output will be numbers smaller than 0, lower than 0, negative numbers expressed in dB in this logarithmic scale in decibel. So in this case, we just change two simple parameters and we start the geocoding, and we see that for Cosmos Sky data, even if they are very high resolution data, we don't need the ground control points. And nevertheless, we will get a pixel precise geolocation of our data. This is another advantage of SAR data, thanks to the way how the SAR is designed, and the sensor shall be very precise in time. At this point, time is the only driving factor to the accuracy of our geolocation, and nowadays we can obtain very accurate absolute geolocation accuracy of our SAR data even without ground control points, and even for the very high resolution data we are processing now as Cosmos Sky. After the geocoding, the last step, as I said, is to compare pixel by pixel the time series of our data and to extract some statistical information. For instance, the mean backscatter we get in 8 images, its variation, step-by-step variation, minimum, maximum, and the span, so the amount of variation in the whole season. And we will generate also a full-score composite image out of 3 specific multi-temporal features. After completing the process, we will be able to save our results. So all the workflow is generating the data in a temporary directory, because of course through the workflow we will generate a lot of intermediate results. But typically we are not interested to the intermediate results, but only to the time series of the backscatter and to these multi-temporal features. So if we are interested only to these outcomes, we will of course delete the temporary files, and we will be allowed to specify the name of the files we will consider as main result. So in this case, I will store all the results in my webinar MECOM directory with Cosmos SkyMed multi-temporal feature. So all the other files will be automatically deleted by the workflow. So finally, this is the result of my workflow. As I said, this is a multi-temporal, is a false color composite image of our area derived from the coefficient of variation from the minimum value and from the maximum change of backscatter in my image. This is one possible combination. We will see other possible combinations. We see already that we have a lot of information. So, for instance, a minimum variability of our backscatter in this area that we can recognize as a river, and also in the aquaculture. We have no variability of the backscatter. We have very strong backscatter over the man-made features, and we have different type of variations of the backscatter in the different fields. And, for instance, we can look at one of the images that has been generated by our workflow. But we see that basically the whole workflow generated a list of results. All the results are stored within a single meta file. This meta file includes both the backscatter time series. We see we have, again, one image for each of the acquisitions. These images have been registered, filtered, multi-looped, speckle filtered, geocoded. So all the workflow executed and created these images. And additionally to the time series, we have the multi-temporal features. The mean, the average of the backscatter, the maximum single date variation, maximum backscatter minimum, the overall variation of the backscatter, so the difference between the minimum and the maximum, and the coefficient of variation. We can, for instance, select 3 dates, the first, the second, and the third date, to create a false color, another false color composite. Here we see what? We see basically that areas with no temporal variation of the backscatter show up in black, gray, white. So we distinguish, for instance, very well the river, very well the aquaculture, but also very well all the man-made features that show up in gray levels. Rice fields are changing a lot, and so we see that, for instance, rice fields that already where some plants were available, were existing at the start of the acquisition of the time series, are already showing in red. That depending on the stage of growth of the rice, we shift from red to blue to yellow, and this color coding relies with the stage of growth of the rice. Of course, we can get a number of images out of 8 acquisitions. So we can compose a lot of false color composite. Is difficult to represent 8 images in one single representation. So what we can use are time series analyzing tools in SARscape. So you can select the raster time series analyzer, and for points of interest, we can get a full representation of the time series over the 8, in this case, acquisitions. So we can start the time series analyzer, and in this case, the first pixel selected is in the center, but we can, for instance, look at areas like this reddish area here, and for this area, ask to plot the time series. So for that location, basically, here we have the full time series of the backscatter. We see that we are around between -8 and -20 decibels. So you see here, this is the flood of the rice field, and here we start the growth. We start to follow the growth of the plant. The plant is high here, so at this point is so high that our X-band data almost not penetrate through the plants, and our surface is very smooth. So we see a decrease of the backscatter when the plant reaches the full growth, and when the rice corns are starting to grow and to mature, we see again here an increase of the backscatter due to the growth of the single seeds. So basically we can relate all the single changes in the backscatter to events in the growth of the plants. And here, of course, we are before the preparation of the fields. So here is the start of the watering of the different fields. Of course, if we move to other locations, for instance, for this time series, we can change different parameters for the visualization, or for instance, also the name of the annotation. We can create the documentation of the time series using these tools. And look not only at the time series, so at the variation date by date of the backscatter, but for that pixel, see which is the average backscatter, so minus 11 dBs, the span difference. So we see that from this value, the minimum and the maximum, we have a variation of about 13 dBs. So agriculture is changing a lot in terms of backscatter through the whole growing of the plants. Something that is not happening in, for instance, in the aquaculture areas, as well as in the man-made features. So we have here much stronger backscatter, but much smaller variation. Of course, as said, we can compare the time series of one location with time series of other locations, other types of rice. Here we select an area in the bluish area, and we see blue means a shift in the time of these time series, and we see here exactly that the growing of the rice started a bit earlier. So instead of in the red time, here in the blue time we had already a very strong backscatter. And we can repeat this process for other locations and see that we have different timing of the temporal signature of the rice, but very similar shape, because again the shape is driven by the process of growth of our plants. So for instance, we can even design specific classifiers based on the temporal signature of our plants and try to match this temporal signature with what we measure in our. If we go to other areas like watering the river, of course we will get different time series. Different means in this case, instead of being around minus 10, minus 15 dBs, we go down to minus 20 and more dBs, so very dark reflections. Water is very smooth in this case, and we get very little reflection from the water. And we see that also the variability is much smaller. Instead of 13 dBs of variability, here we have maximum 2 dBs, so water is very constant. This is happening for river, but the same happens also for the aquaculture areas. So we can use this information to discriminate in a very simple way, for instance, rice fields, even if they are also sometimes flooded, to areas that are permanently flooded, like, of course, the river, but also the shrimp farms. If we move to man-made features, we see a similar small, very little variability with the time, but of course instead of small backscatter, we go up to minus 10 dBs from minus 20, 22 dBs. So much stronger reflectivity, as we see in the image, but little reflectivity, a little variability in the time. So we will use these ingredients, these concepts, to discriminate the different types of land growth. We can, for instance, create another false-color composite to see what is happening at the end of the growing season. We take the last 3 images and we create this image, where again we see the same behavior in the man-made features, in the water areas, in the agriculture and in the river and the little channels, but we see much smoother colors in the fields. That means that at the end of the season, more or less all the plants got at the maturity. together. We don't see many spatial variabilities. Of course, we see some smaller change in timing, but not as dramatic as at the beginning. And we can investigate the single multitemporal features. So for instance, we can look at the average backscatter all through the whole time series, and we see, as we see also in the single images, that the average backscatter of the fields is very similar, but very different from the water areas and very different from the man-made features. Variability, so the span of the difference between the minimum and maximum backscatter, is bringing us additional information. Of course, we saw different timing in the growth of the different rise fields, and so we see some field has a smaller span, so it's a bit later respect to these fields that have earlier rise. We can look at all the features, and in this case, basically we will concentrate on the average backscatter and on the span, in the difference between the minimum and maximum backscatter. Using these two channels, we can exploit, for instance, a very simple classification scheme. We can use a rule-based classifier, so use ENVI features about decision trees, and we will create a new decision tree, very simple, to discriminate basically 4 classes. So we want to discriminate 2 types of, let's say, early and late rise, man-made features, and water areas. That means rivers, but also aquaculture. Which parameters are we going to exploit? In this case, very simple. We don't need to go into the details of the full time series. In this case, we are just looking at the main classes. So we can use the average backscatter and ask if we are looking at pixels with a small average backscatter. If this is the case, and we can set up here a threshold related to our measurements. We saw in the case of water, we see something about -20 dB or less. So if the backscatter in average we read for a pixel is smaller than -20 dB, in this case we call this pixel water. If vice versa, it's not small the backscatter in average, but is in average very strong, about -10 dB or more, we saw from the time series that we are looking at the man-made features. So if the backscatter in average is very big, yes, we are looking at this type of class. If we are in a case of, say, medium backscatter, now we can use the span to discriminate 2 types of rise, early rise and late rise. So it's a very simple classification scheme. We can, for instance, also use the parallelepipedal classification tools of ENVI, but this is basically, or we can use more sophisticated classification schemes. But I wanted to show here the power of the SAR data and of simple statistical indicators derived from our time series. So we are compressing all these plenty of information in 2 parameters, and these 2 parameters are enough to tell us everything about the history of our data and of our terrain. So this is basically the result of our classification. We could improve it a bit using some morphological filters, but we see that, I would say, we just visually we can be very happy of the results of this very simple classification scheme that is distinguishing very well the river, very well the agriculture from the man-made features and from the 2 types of rise. And we can switch, for instance, the first type of the first class of rise, early rise, and see how it matches very well with our fields, and look at the second one that corresponds to the yellow fields we saw in the first composite. So this basically concludes my presentation. And now the floor is open to the questions to the experts.